Hello, welcome guys. So this is our day 2 history and types of neural networks. I am your educator Suyash. So let us first revise what we have studied earlier. So what we have covered. So till now we have covered the basics of deep learning. We have covered what is deep learning, how it basically works, what is deep, what is the meaning of deep inside deep learning. We have covered this. We have covered different types of neural networks like ANN, CNN, RNN. We have just covered the basics. So this was our agenda overview. We have covered what is DL, how DL works, what is the key differences of ML and DL, supervised versus unsupervised learning, and real world applications of deep learning. We have covered low level features, what are early layers in a neural network, what are middle layers in neural networks, what deep layers do in neural networks. The last one, basically, what last neural networks deep layers do in neural network. And we have also covered haven't covered non-linearity. We will be covering in day 2 or day 3. We have covered automatic feature extraction. We have covered scalability. We have covered these were the key characteristics we have covered. We have covered difference between machine learning and deep learning. Basically, machine learning is more towards probabilistic model and deep learning is more towards neural networks, and AI is the superset of all of them. And we have covered the differences, model type, different models like supervised learning, unsupervised learning, reinforcement learning, which comes under ML. And then we have also covered the DL transformer models, recurrent neural networks, convolution. We have just heard these words. Sometimes just listening to and understanding the word is very important. Then we can explore later on these topics. We have covered the ML and DL differences and how the data giving data gives the accuracy, the efficiency of the model, the predictive performance of the model. And then we have covered feature engineering, computation power. DL requires more computation power than ML, and then training time is also high in deep learning. Interpretability is like basically deep learning models are black boxes models, so it is harder to interpret it. But now today they are upcoming fields like explainable AI, which are helping to convert these black box model into white box model. And then we have seen what are the examples and applications, and we have covered the difference between supervised and unsupervised learning. Basically, in supervised learning we pass labeled data set, and in unsupervised learning we don't pass labeled data set. And then we have seen applications of neural networks. So what we'll be studying in day 2 lecture. So in day 2 lecture we will be covering the history and types of neural networks in detail. In detail we will be covering the history and types of neural networks. So basically let's just read these things, and then it will be very helpful for us to understand in later phases. More we will dive deeper into them. Let's understand. We should actually cover the history parts. That helps in growing the knowledge how things processed, and it helps us to understand how people started to work on things, what were the research gaps, and how the scientists and researchers fill those gaps, and then it helps us basically. So in 1950, Alan Turing introduced the concept of machine. Alan Turing introduced the concept of a machine that could simulate any computation process, leading to Turing test, which paved the way for AI. In 1957, Frank Rosenblatt developed the perceptron. Perceptron is very important for us. We will be diving deep into this. Perceptron is the basic artificial neuron unit, which is basically inspired by biological neuron. So it is an artificial neuron unit inspired by our biological neurons, which are present in our brains. So perceptron, this we will be covering in detail because it is a very important part. So Frank Rosenblatt developed the perceptron, the first artificial neural model which mimicked human brain neurons. It could only solve linear problems and was limited in scope. In 1969, Marvin Minsky and Seymour Papert demonstrated the limitations of perceptron, particularly its inability to solve XOR-type problems, non-linear problems. This caused a temporary decline in neural network research. In 1980s, the revival of neural networks came with the development of multi-layer perceptron, MLP, which we call MLP in short, and the backpropagation algorithm, which allowed training deeper networks and solving more complex problems. You basically remember these words because these words will be occurring in your whole deep learning journey. These words will be coming again and again, and we will be diving deep into it. So in 2006, Geoffrey Hinton and his team initiated a revolution in deep learning by improving neural networks through unsupervised pre-training. Unsupervised, as I've told you guys in last lecture, that unsupervised learning basically are the data which haven't been labeled. We are just passing it to the model without labeling them, and model itself is understanding the data on its own and predicting it. So unsupervised pre-training and fine-tuning deep networks. So fine-tuning deep networks leading to modern advancement. So basically we basically study two types of tuning, like pre-training and fine-tuning. So pre-training. So in pre-training, basically we are constructing a model and we are training it from scratch without any pre-trained weights. Weights are basically they are the constant terms which are not constant term. Basically they are the slopes which are given to the a perceptron and with a bias term, and they are trained with the help of backpropagation, and many algorithms are also there which helps us to train the neural network. So pre-training is that we are training it from scratch. We are just randomly assigning some weights and then learning from losses and then training the model. And fine-tuning is that we have some pre-trained weights. Basically the models are available which have been trained on a large amount of data set, like many models are trained on ImageNet dataset, and there are many data sets which are available, which are a large data sets in which big models are trained, and then we are basically fine tuning it. Basically training, we are just taking that pre-trained model to our system or hardware devices and then giving more input to it and training it accordingly to our needs. So basically this is also it's mostly people are now fine tuning with the model according to our needs, because there are very lack of hardware resources in small startups and small places. So basically we are we are taking importing pre-trained weights, and then we are fine tuning it according to our needs. So Geoffrey Hinton and his team initiated a revolution of deep learning by improving neural networks through unsupervised pre-training and fine-tuning deep networks, leading to modern advancement. In 2010, GPUs and large-scale datasets like ImageNet, as I told, ImageNet is a very large dataset, allowed neural networks to train more efficiently. Technologies such as convolutional neural networks and recurrent neural networks became widely used. So this was a basic coverage of history and early developments of AI and neural networks. So we will be so you just remember these words like unsupervised pre-training, fine-tuning, perceptrons, backpropagation algorithms, multi-layer perceptrons, and we will be diving deep into it. And then we move to evolution of AI and deep learning, AI versus machine learning versus deep learning. Basically this thing we have already covered, so let's revise it. So artificial intelligence encompasses the broader idea of machines mimicking human intelligence. Example, voice recognition, autonomous vehicle. Just remember the schematic which we learnt in the last lecture, AI. And then machine learning is a subset of AI, and then deep learning is the subset of ML, and hence it's a subset of artificial intelligence. Machine learning, a subset of AI that focuses on building models that allow machines to learn from data. Like some of the machine learning algorithms are decision trees, SVMs, random forest. And then we have deep learning, a specialized field of ML focused on using neural networks with many layers to model complex data representations. So this we have covered. I actually added many pages. So example, image classification of deep learning, basically image classification with convolutional neural networks, language translations with RNNs. So these are basically the differences between artificial intelligence, machine learning versus deep learning, so which we have already covered a lot about this topic. We have studied many points like data, what amount of data is required in machine learning, and what amount basically the performance of ML and DL models. So we have covered these things. So key milestones in the evolution, we will be looking to key milestones in the evolution of this artificial intelligence field. So in 1956, John McCarthy coined the term of artificial intelligence. In 1990s, the rise of machine learning algorithms such as support vector machine, it is a very important algorithm, and random forest, SVMs and random forest. Those who have studied data science, they must be knowing these algorithms. These are very important algorithms. And in 2000, deep learning began to outperform traditional ML algorithms in areas such as image recognition, speech, and language processing. Basically, deep learning outperformed traditional ML algorithms because of the hardware innovations which came. Hardware resources were available, and also the data sets which got available, which now are easier to basically were available to us, a large amount of data set, because deep learning models feed on a large amount of data set. So present deep learning applications range from healthcare to finance, gaming, and self-driving cars. It has captured whole domain of engineering, like it is in mechanical engineering. Deep learning models are applied in civil engineering. In every part of engineering, deep learning models are applied. So overview of different neural network types. So we will be basically diving into different neural network types. So there are many different neural network types, like CNN. Like first we have ANN, artificial neural networks, and then we have CNN, convolutional neural networks, and then we have RNNs. So these are different neural network types of neural networks. There are more neural network types, like which I earlier we have studied, like here we have looked like multi-layer perceptron. We can consider it also a type of neural network. So let's make a list of types of neural networks. Types of neural networks. So we can count multi-layer perceptron also. Multi-layer perceptron as a neural network. Then ANN, artificial neural network, and then CNN. So basically artificial neural network, we call it ANN in short. And then we have a convolutional neural network, neural network, which we in short called CNN. And then also we have a recurrent neural network. It's recurrent neural network, RNN. Let's dive deeper into it. And there are many some more neural networks, like If I remember, GAN is also a type of neural network. So the full form of GAN is generative adversarial network. So basically GAN is used for producing synthetic data, like producing an image which don't exist, like creating a face image or a scenery which don't exist in real, and we are just generating synthetic data from those models. And we will be looking into this. And other types of neural networks also include autoencoders. So autoencoders are also a type of neural network. So basically these are the different types of neural networks. Like let us cover these types of neural networks in detail. So multilayer perceptron, let's make it here. Multilayer perceptron. Multilayer perceptron includes a lot of perceptron. Perceptron basically, let's just cover it in short. What is perceptron? And we'll be covering this in detail. Perceptron is basically it's an artificial neuron which have it's like a neuron. Circular thing is like a neuron, and it have W1, W2, and W3 are the different weights. We can include bias here only. Let's consider this as a bias term. And then we have an activation function. So W1 and W2 are the basically the weights, and bias is the constant term, and then it is passed through activation function. So x1 and x2 if are the inputs, then x1 W1, x2 W2 plus bias is your z, and which is passed by an activation function. So this thing is basically z is passed by an activation function. Let's consider f to be an activation function and z is passed. So the solution of this thing will be passed to other perceptron. So if this thing is a perceptron where x1 and x2 are the inputs, W1 and W2 are the weights. Basically these are the perceptron parameters, are the weights, and B is the bias. So basically z is the output of these x1 into W1 plus x2 into W2 plus bias, which is passed from activation function. F is the activation function. So the output of all of this is passed to another perceptron. So this is one perceptron unit. Perceptron unit. So from this one perceptron unit is connected to other perceptron unit, and the output of this will be passed to another perceptron, and the same procedure will take place. There can be a lot of many weights like W1, W2, W3, W4, W5, and then we have a bias term, and this forms an equation basically. And this is the input parameters like x1 and x2 are multiplied according to their with the weights W1, W2 weights, and then a bias term is added, like if you remember an equation passing from origin so this is y-axis, there is y-axis and x-axis, and then equation is like y is equal to ax plus c. So if it is passing from origin, then we write it y is equal to ax, and if it is passing from some c, then we can write it as y is equal to ax plus c, where c is this is c basically. So this is what we called as bias. So if the equation is not first passing from the equation, C is the basically the bias. It is passing from distance above x, some distance above x-axis. So this is basically the basics of perceptron. So the multi-layer perceptron means like output of one perceptron is being passed to other as an input, and then there is a whole tree, a whole bunch of perceptrons which are passing they are taking the inputs from other perceptron and then passing the output, their output, to other perceptron to give results. And they have their own parameters like W1 and W2. They have they have different parameters of their own. So basically this is the multi-layer perceptron, and it is used, it is basically a model which is used for deep learning models. Same goes with ANN. Similarly ANN is also based on similarly ANN is also like it is also a layer of neurons. So inputs are passed like x1, x2, x3, x4, and these inputs are passed to each of the layer like this. So you can make these things by your hand and understand these things. These are very basic things. And then there is another layer, like suppose we give it a 3 neurons, and so with this we have made already, and it goes here, it goes here, and then it goes here, it goes here, it goes here, and then this. And if it is a binary problem task, which will be understanding what is binary and multi-class classification, so this is passed to 1, and then there is an output to it. So basically artificial neural networks are basically a model where x1, x2 and x3 and x4 are the input, and then we have this thing, these circles we consider that as neurons, artificial neurons or perceptrons we can also say. But keep in mind that not all artificial neurons are perceptron. Keep this thing in mind. But perceptron is an artificial neuron, but not all artificial neurons are perceptrons. There are other also artificial neurons. So basically this thing is a neuron, this thing is a neuron, this thing, and these all circles are neurons. And then we have weight parameters like W1, W2, W3, W4, W5, like this thing goes on. And then we, for each a neuron, we will get an equation. Like if we scale this down for easy explanation, like it is getting tougher for me to explain everything, so let's scale it down to something basic, like 2 input model x1 and x2, and then it goes to basically this thing to a model input of 2 goes to 2 neurons, and then it is passed by a single neuron, and then output. It will be very easy. Just I've scaled it down to just 2 neurons instead of 4 neurons, and then 3 other neurons, and then from a 2 hidden layer to a single hidden layer. So basically this input x1 will be passed to x1, x2. Okay, so basically let's try something new. Let's first use different pen colors for better explanation. x1 and x2. x1 and basically x1 is passed to both neuron, and then not this color, this color is better. Yeah. So if we say like x1 is passed to both of these neurons, then the equation which will be formed will be like w1 x1 and then x2 is gone to this equation is for both inputs. Basically this is the equation of a neuron. This is the equation of a neuron, remember this. So w1 x1 plus w2 x2. So this is, if we consider this as a first neuron, then bias term of first. Similarly for the second neuron, equation is, this is the equation for first neuron, and then this is the equation for second neuron. So w21 x1 plus w2 x2 plus bias term 2. So this is the basically the outputs from both of these neurons. Basically these are the linear equations. So these linear equations will be passed to activation functions. Activation functions are basically they are used for covering the non-linearity in the model. So like in ideal world case, there are no linear data. There is nothing linear in linearity in our nature. Basically everything, nature's everything is non-linear. There is not a hidden symmetry, there is only a non-linearity. So activation functions are basically used to cover those non-linearity in the data set. So the output of Z will be passed to the activation function, and the final output which is coming, like we can call it a capital Z. The final output which is coming out of both these the capital Z which is coming out, and then this is passed to another final output neuron. So this will also have an equation, like we can call it Z dash, and the equation of it will be like w3, if we call Z1 and w3 2 Z2 plus the other bias term of this particular neuron, and then this thing will be also passed. There are many different activation functions according to our purpose of use, so that we will be covering those also. So this is how neural networks work. So basically these are the linear equations which are passed in the deep learning models, which are passed from input like x1, x2 and x2 to the neurons, different neurons and different hidden layers. Every neuron has an equation which it gets basically the inputs, and then a linear equation is formed. The output of linear equation is passed to the activation function. Then a final output after passing from the activation function becomes the input to the other neuron. So basically there is a whole process which we can write as first input is passed to a neuron. Okay, then what happens? A linear equation is formed. Basically w1 w2 and all these things like w1 w2 1 w 1 2 w1 w2 2 and w1 3x, and these things are basically the model parameters, including the bias b1 b2 these things are basically the model parameters which will be randomly assigned by the model at the start of the training process. And then after every epoch, you might be knowing epoch if you have studied the machine learning. So basically after every training iteration, the weights will be changed due to the back propagation algorithm, if we are using that algorithm, and then the model will be learning the parameters will be changed, and new weights will be assigned to effectively understand the data set according to the to effectively understand the data set, the model weights and biases. The model weights and biases, basically the whole model parameters will be changed according to the data set to effectively fit into the data, to effectively understand the data. So a linear equation is formed which will be passed to an activation function, and the output from it forms the input for the other neuron. So basically these are the process which is followed. Basically this process is being followed by every deep learning model. This is the basic process which every deep learning model follows. And how the training is processed, it is processed like this thing only. So random weights are assigned, w1, w3, w2, w3, and these are the random weights, and b1, b2, b3, b4, these are the random biases which are assigned at first, and then the model is trained, and these weights and biases are basically changed according to the losses, and then they are assigned the way to effectively fit the data, so for a proper training. So basically this is the basic of artificial neural network. So if we add a page for convolutional neural network, so basically we have understood what is multi-layer perceptron, what is artificial neural network, and then we'll be diving deep into what is convolutional neural network. So basically what is convolutional neural network? Okay, what is convolutional neural network? Convolutional neural network. Yes. So basically like this we have understood what is artificial neural network. So basically if we divide this thing, like we can consider this as an input layer. This is x1, x2, x3 and x4 are inputs, as I told earlier. So basically, can we consider this as an input layer? Fine. Can we consider this thing as our hidden layer? Keep in mind what I did here is basically scaled down version of this thing. You can do the similar thing with this. Basically you can do same thing like this we did here also. It's basically we have to randomly assign weights to each neuron and a bias. Basically randomly assign each weights to each these lines, and then accordingly we will be getting and assigning a bias, and then we will be getting an equation, and then we will be finding the output, applying activation function to it, and passing that output as an input to the other neuron. So so what we were doing, we were considering this as a hidden layer, then basically input layer this thing, and then we are considering it as an hidden layer. We can say this as a hidden layer. We understood what is hidden layer. Hidden layer is basically the layers between input layer and hidden layer is basically the layer between input layer and output layer, and then this is the second hidden layer, and then this we can consider as an output layer, because it will be giving us the final output. So in in convolutional neural network we have different layers. So let me first make it clear, like first we will be having an input layer, as you know. First we will be having an input layer, then the input data points are passed to convolutional layer. Basically this whole thing is a convolutional neural network, and then this layer specifically is convolutional layer. Convolutional layer, and then passing it to the pooling layer. This is also a layer which we'll be studying. This is pooling layer, and then we have a fully connected layer, fully connected layer, and then final layer is output layer. Mind it, basically fully connected layer is this layer, these layer basically with neurons. So we can also say these layers as fully connected layers. We'll be covering these different kinds of layer in details. So input layer, convolution layer, pooling layer, fully connected layer, and output layer, these are the basic layers in convolution neural network. We will be covering each of these layers in detail, and we have what are the different applications of CNNs. Basically CNNs are used in image processing, the different fields like medical imaging. It is growing field like OCR. OCR is basically object character recognition. Object character recognition and different recognition and different applications of these CNN models include in OCR. We can say like number plate detection, basically recognizing the number plate, the number on the number plate. And in medical imaging, like basically we can segmentation purposes, segmentation of different body parts, of different body parts in different modalities, like different modalities like CT scan and MRI. So the purpose of CNN are basically in image processing world, in medical imaging, OCR, and in basically things which like in today's world, like fake image detection, classification purposes, image segmentation, instant segmentation, semantic segmentation, and then object detection. Basically we are having bounding boxes for object detection, and one of the biggest application, like you must be knowing about Tesla, the self-driving cars. So basically these image video things are dealt by CNNs. So CNNs are very important neural networks. So moving next to RNNs. RNNs. We must add a page here. What is RNN? The full form of RNN is recurrent neural network. So let me make a basic model of an basic RNN model. So X1, X2, these are basically input, so we can call this whole as an input layer. Then a hidden layer, and then another hidden layer. Let's suppose make 3 neurons, and then an output layer basically. Okay, so let's complete this thing. completed, yeah. And then joining to the output layer. Last one is our output layer, and the center ones are our hidden layers. So basically, in what happens in RNN is like the output of any layer, like of output coming from these layers, are again fed to the backward, what we say, like the adjacent layer, which is in the back side. So it's like in other neural networks, like we are feeding our output data to next hidden layer, but in RNN it happens like the data coming from this hidden layer 2 are fed again to the hidden layer 1. I hope you understand. In other neural networks, data coming from hidden layer, output coming from hidden layer 2 are passed forward. But in RNNs, the output of hidden layer 2 are again passed, or any hidden layer, if there is very deep neural networks with thousands of hidden layers, then the output of any hidden layer is passed to another hidden layer, which is in backward direction, which is in back, basically. So this model is used a lot in NLP. Basically, the example of RNN model is LSTM, long short-term memory model. So applications of RNN is in NLP. What is NLP? Basically, NLP is natural language processing. Now we have moved to much broader topic of LLMs. So yeah, basically initial days we used to have NLP. It's not a very historical thing, but till today also we are using NLP a lot in different kinds of projects. So this is basically the basic of a recurrent neural network. So just you need to understand for now that the output of a hidden layer is given to another layer, which is basically which is like a output of hidden layer 34 is passed to hidden layer 21. So basically we are passing the output of not just feeding forward, we are passing the output to backward layers. And then we have another like GANs. So another neural network is GAN. So basically GAN are generative adversarial networks. So what GAN does is basically GAN generates images, videos, music, and it basically have two types of neural network types in it. Basically the encoder part and discriminator. The work of encoder is to encoder and basically decoder, and discriminator is also there. So basically encoder's work is extracting feature maps. You will be knowing details about feature maps, feature vectors, and prototype vectors, representative feature maps basically. And decoder is decodes those features extracted from encoder. Basically it decodes the features extracted from encoder and adds special informations which were lost during encoding to it, and then gives the output. And discriminator work is basically in GANs, discriminator is used to
In GANs, basically encoder and discriminator works, but as I am telling about in encoder, it is obvious to tell about decoder. So in discriminator, basically discriminator's work is to discriminate between the real image and label it as a real, and fake image to label it as a fake. So it's an obvious work of discriminator to tell that if a real image is passed from it, then it is a real image, and if a fake image is passed to, then it is a fake image. But we have to fool discriminator to make our model better. So if a discriminator tells fake image as a real, then you must understand that how better quality image or synthetic image is produced by our model, that we can fool discriminator to label a fake image as a real image. So just we have to fool the discriminator to label a fake image as a real image. So we are basically working on this to decrease the discriminator loss and to label a fake image as real image. So this is basically the work of discriminator, and basically GAN is main thing about GAN which you must know for now is it is used for synthetic data generation. It can be, the data generated can be an image, video, music, etc. And this we have covered about GANs, and one more I think is left. What is left? Yeah, autoencoders are left. So the work of autoencoder is also a type of neural network, and autoencoder's work is to compress data without losing quality. So just remember this about autoencoders, that autoencoder's work is to autoencoder it's work to compress data without losing quality. It basically compresses data without suffering from the data quality. So just remember this about autoencoders, and then we have covered overview of different neural networks. We have covered many things in detail. This is the basic code, so let's just read them once and you will understand.
So here, artificial neural network, a type of neural network consisting of layers of artificial neurons, also called perceptrons. So basically I told you, as you remember, this is AN, and basically these are the neurons. The circle thing is basically neurons. These are artificial neurons, and let me remind you once that I told all artificial neurons are not perceptrons, but all perceptrons are artificial neurons. So basically this thing you should remember here, also called perceptrons, but basically not all artificial neurons are perceptrons, but all perceptrons are neurons, artificial neurons. So a type of neural network consisting of layers of artificial neurons. They are fully connected networks used for general tasks. So what is fully connected? Basically they are fully connected means that they all are connected to each other. So basically they are fully connected to each other, and they are fully connected, used for general tasks like task. So architecture typically consisting of input, hidden and output layers. Yes, we have understood this. Use cases used in pattern recognition, prediction tasks. Yeah, we understood this. Example, this we will be running our code in later part of the series. So import these are basically the TensorFlow is the library which we are using. They are basically we will be covering TensorFlow, maybe PyTorch also. And then advantage is easy to implement, good for structured data. Limitations, limited in dealing with sequential or spatial data. Limited in dealing with sequential or spatial data. Spatial data comes in having a lot of dimensions to it. In image processing terms, spatial data is basically a lot of data which are not considered as a features basically a lot of big data which is not considered a big image where there is in foreground there are features, in background background thing is not considered as a feature, so it can be considered as spatial. So limited in dealing with sequential or spatial data. And convolution neural networks, a specialized type of neural network designed for image data. Yes, we understood this, designed for image data, which automatically detects hierarchies in images. Architecture, yeah, we covered the architecture. Those layer includes convolution layer, input layer, then convolution layer, then pooling layer, then fully connected layer, and then output layer. We understood the use cases, and then we know the advantages also. Like here, best for images and spatial data. Like in image, I made you understand about the spatial data. It is a very big data covering many things in foreground and in background. And best for image and spatial data, and low computation cost with high accuracy. Difficult to interpret the model. Limited applications in non-image data. And recurrent neural networks, we have understood they have a memory to remember. Designed for sequential data, they have memory to remember previous inputs, which make them suitable for time series data. So RNNs are basically used in time series data analysis. Time series data analysis are used in forecasting, like in flood forecasting case. LSTM are used basically in RNNs are used in flood forecasting, time series data, stock market predictions. So they have a memory to remember. Memory is basically those things like I told now, the input of the output of a hidden layer is again passed, so basically it becomes the memory to it. We will be covering recurrent neural network and all these neural networks in detail later on. This is the code of it. And architecture, we have seen neurons connect to the next layer but also to itself. Includes recurrent layers where each neuron connects not only to the next layer but also to itself. Language modeling, time series prediction, time series prediction, speech recognition, language modeling like NLP. And then idle for task involving sequences. Text and audio, we have a sequence like a word token to be passed, and another word which in speeches we need to be obvious, like we cannot just get random sequence of words. Those words create a sentence and the sentence should be meaningful, so sequence is very important. Limitations, training is difficult due to vanishing gradient problems. If you have learned ML, you must be knowing. We will be covering this vanishing gradient problem. Autoencoders, as we told, autoencoders are used for basically compressing the data without losing its quality. So in neural networks used for unsupervised learning to encode data into a compressed format and then reconstruct it. Includes an encoder. Encoder also I explained you. Basically it is the way of feature extraction, giving a feature map or a feature vector. So includes an encoder, compresses input data, and a decoder reconstructs original data from compressed data. Use cases, dimensionality reduction. Sometimes there is a lot of a very big dimensional data with a lot of parameters, and so we sometimes need to decrease the dimensionality for the ease of our model and for ease of our computational resources. So dimensionality reduction is important. Anomaly detection, data denoising. Advantages: efficient feature extraction, reduced data redundancy, and limited to reconstruction task, and requires careful tuning. Generative adversarial network, basically it's a type of generative model where two networks, a generator and a discriminator. I explained autoencoder. Sorry, I made a small mistake here. In GANs I explained discriminator part, but I haven't explained generator part.
So basically I explained encoder, basically encoder and decoder there, and a discriminator. So in GANs it is generator and discriminator, sorry, my fault. So basically in GANs there is generator and discriminator. So basically in what generator does, it generates images, creates fake images, or basically music or some kind of text, and the work of discriminator is to like I told, discriminator is to discriminate between its real or synthetic data. Synthetic data is basically a fake data which is made by our model. So the work of a discriminator is to discriminate. So we in GANs basically we have to fool the discriminator to label the fake or synthetic data as real. So we have to achieve that level of accuracy by decreasing the discriminator loss. So basically GANs type of generative model where there are two networks, a generator and a discriminator. What is the work of generator? Creates fake data as resembling real data, and discriminator identifies whether input data is a real or fake. Okay. So use cases: image synthesis, data augmentation, style transfer or creative applications. Advantages: generates highly realistic data, prone to instability during training. Limitations: prone to instability during training and requires large computational resources. So this thing we have covered. So this part I think we will be covering. This is the detailed version of artificial neural networks, the basic building block, which we fortunately have covered here, the basic building block, and this thing we will be also covering in the next part of the lecture. And also we have covered this thing, like I have told the equation, the linear equation, then passing to an activation function, to covering the non-linearity in the data set. And this schematic is the representation of how this is how the experiments were done on a cat, and basically electrode was used and placed in different parts of the cat brains at different neuron points, basically in different brain parts where different neurons were present, and different images were shown, like a tilted line, sometimes a horizontal line and a vertical line at different parts. Basically what is oscilloscope showed different kinds of reading, which showed that different brain parts respond to different images differently. So this was the key takeaway which scientists got, and this is how the things began to run. And this was the complete day 2 lecture of our deep learning course. So day 2, what we have covered, just a recap of it. So we have covered history and types of neural networks. What were different types of neural networks? We have covered MLP, multi-layer perceptron. We have covered artificial neural networks, in which in artificial neural networks we have covered the different kinds of layers, how the equations are generated, how it is passed to the activation function, and then how the activation function works. And then we have covered convolutional neural network. We have basically understood the basic architecture, how convolutional neural network architecture is, like convolution layer, pooling layer, then we have fully connected layer, and then we have studied about RNN, recurrent neural network. Then we have understood about GANs. By mistake we have covered encoder and decoder also, but in GANs basically GANs have two models, generator and discriminator. We have understood about generator, and we have understood the discriminator, how we have to decrease the discriminator loss so that we can fool the discriminator to label the fake image as real image. We have to fool the discriminator so we can generate a very good synthetic and fake data. And then also we have also studied about encoder and decoder. Basically encoder's work is for feature extraction, and decoder's work is for adding the spatial data and getting the purpose, basically what purpose we are using decoder. So basically to get back the data, to reconstruct the original input to get back the whole data from the feature map extracted from the encoder. And then we have studied about autoencoders, whose work is to compress data without losing quality. And then we basically, this was our and then we slightly again delve into the history part, like what experiments were made by scientists. So they used a cat and an oscilloscope electrode they put on different brain parts and showed different kinds of images, different kinds of shape lines to the cat, and noticed the oscilloscope readings, how different part of brains reacted to different kinds of shapes. So they understood how neurons react differently. So basically this was the basics of day 2 lecture, and then we will be moving forward to another parts of the lecture soon. So thank you, have a nice day.